with 15.5% defective files, and GM1 is the largest one. We have like 11 instances, 11,000 instances at 18 or 19% defective, and we have also PC1 and MC1. Yeah, all datasets share static code metrics as features, things like lines of code, cyclomatic complexity, and hasted measured. Our pipeline starts with data pre-processing, normalization, and label cleaning. We then train and evaluate 8 classical models as random forest, gradient boosting, ADA-boost, SFME, and logistic regression, and other models, and this decision tree. On the deep learning side, we use a multi-layer perceptron as a baseline ANN and an LSTM network. Our primarily evaluation metric throughout is the F1 scores, which balances precision and local critical for imbalanced settings. Looking at the GM1 datasets first, the largest and the most imbalanced among our 4 ensemble methods perform outstandingly. Decision tree, ADA-boost, and gradient boosting all achieve perfect F1 scores as result like 1. While random forest reaches 0.99, logistic regression also performs well at 0.986. The clear performer here is Navier-based at only 0.37, which struggles due to its features independence assumption. On KC1, we see a very similar patterns as the GM1. And moving to the PC1, which has a lower defect rate of 6.9%, ensembling methods against dominate decision tree, ADA-boost, and gradient boosting achieve perfect F1 scores, while random forest reaches 0.968. However, notice that SFME drops significantly to only 0.30 here. It struggles with the minority class under greater imbalance. And now the MC1 is a completely different story with only 0.7% defects instances. This is a several imbalanced datasets, and every model suffers. The best performer is the random forest with an F1 scores of just 0.57. Navier-based actually achieves a higher recall by prediction more positives, but at the cost of very low precision, giving it the worst F1 at 0.13. This slides illustrates that the problem here is not the models, it is the data distribution itself. No algorithm can reliably detect a class that presents less than 1% of the training data without explicit imbalance handling. And for a summary for the F1 scores, we have this table. This table consolidates our perfect scores above 0.99. The yellow cells represent the good performance between 0.90 and 0.98, and the red cells highlights scores below 0.50. You can immediately see the entire MC1 columns contains no green, and as a visual confirmation that severe imbalance affects every model. You can also see that navy base is consistently in the red or with across all the data. Random forest is the most balanced overall. Performed is score 1 on KC1 and 0.99 on GM1 and 0.968 on PC1, and still manages the best score of the 0.571 on the MC1. And for this slide, we have as a comparison of the classical models and deep learning models. As you can see, the PC1 exception in the PC1 and LSTM is 0.79, slightly outperform random forest 0.78. And structure patterns, LSTMs can reveal deeper relationships in software metrics. And for the MC1, that challenges, can we see? Give me back the performances that we get in
Oussama,
MC1. Yeah.
Oussama, you have 2 to 3 minutes more. So can you please try to obey
Yeah.
to the time limits?
Okay, hocam. Yeah, as you can see the results, we can pass to the key findings to be in the time. Let me summarize our 5 key findings. First, ensemble methods, particularly random forest, gradient boosting, and AdaBoost consistently dominates on balanced and moderately imbalanced datasets. Second, we have class imbalance is the primary bottleneck on MC1. Even the best model scores only 0.57. This is a dataset level problem, not a modeling problem. Third, and importantly, LSTM shows a real advantage on moderately imbalanced datasets like PC1, where it achieves higher minority class recall than most classical methods. This suggests that deep learning can capture structural future interactions that classical models miss, but only when the dataset distributions allows it to learn. Fourth, we have the Navy base consistently in their performance across all the datasets and is not recommended for software defects prediction tasks. And the fifth, the ANN, our sample ML baseline performs competitively on a balanced datasets, confirm that deep learning can match classical ML given favorable data conditions. And for to conclude, our study confirms that the classical ensemble methods remain the most robust and reliable choice for static metric-based software defect prediction. However, deep learning, specifically LSTM, is not irrelevant. It offers measurable advantages in recall for moderately imbalanced datasets, suggesting it captures richer patterns that tabular models may miss. For future work, we plan to apply imbalance mitigation strategies such as smooth and cost sensitive learning, explore transformer based architectures, and extend our evaluation to cross project settings and industrial code base. We also intend to incorporate dynamic code metrics and commits history for richer future representation. And thank you very much for your attention. And I am happy to take any question of you.
Thank you for your nice presentation. Is there any question?
Thank you, Özlem.
Okay, we have no questions, so we can proceed
Okay,
to the
Özlem.
next presentation. The second
Okay, Özlem.
presentation is, okay, that's all for you. Thank you for your presentation and participation. The second presentation will be a multi-agent AI pipeline for molecule generation demonstrated with HER2 target protein with Ömer Avşar. Okay, you can start. Ömer,
Hello,
are you
everyone.
there? Okay.
Yes,
You
I'm
can
here.
start presentation.
I will share my screen in a second.
Okay.
I will share my screen in 30 seconds. So I'm sorry.
Okay, that's no problem.
Okay. Hello again. Sorry for the delay. Now I'm sharing my screen. Can you guys hear me?
Yes.
Yes, we can hear.
Okay, thank you. Okay. Okay. So, hi everyone. Thanks for being here. My name is Ömer Avşar. I'm a PhD student in İzmir Katip Çelebi University on computer engineering. And I'm presenting today with my colleague Umut Şanlı. We want to talk about drug discovery, not the chemistry side of it, but the process itself. Why it takes so long, why it costs so much, and what happens when you try to use AI to fix that. We've been designing a pipeline that connects some of the most powerful AI tools in computational chemistry into a single automated workflow. And today, We are going to walk you through how it works and why we think it matters. Let's start with the problem. When you pick up a prescription drug at a pharmacy, you are holding something that took over a decade to develop and costs more than $2 million to bring to market. That's the average. And even then, roughly 90% of drug candidates that enter clinical trials never make it to approval. They fail because they are toxic, because they don't bind well enough, because they can't be absorbed properly. The real bottleneck is right at the beginning. Before any clinical trial, before any human testing, researchers have to figure out which molecules are even worth pursuing. That process, screening, synthesizing, and testing thousands of candidates one by one, is where most of the time and money disappears. 10,000 candidates go in, 250 make it to preclinical testing, 5 reach clinical testing, and 1 gets approved. That's the funnel. And we think that AI can dramatically change what happens at the top of it.
Before we get into the pipeline, let me explain why we choose HER2 as our demonstration target. HER2 is a receptor protein that sits on the surface of the cells. In healthy tissue, it does something pretty simple. It helps control when a cell should grow and divide. Think of it as a switch. Normally, that switch is carefully controlled. But in about 15 to 20% of breast cancer cases, something goes wrong at the genetic level. The HER2 gene gets amplified, and the cell starts producing 20, 50, sometimes 100 times more of those receptors than it should. The switch gets stuck in the on position, and cells start dividing without control. That is HER2 positive cancer. Now, the reason we picked HER2 specifically for this demonstration is practical. It is one of the most well-studied protein in cancer biology. Its structure is publicly available. There are known drugs that target it, which means we have a real benchmark to compare against. If our pipeline generates a candidate molecule, we can ask, how does it compare to what we already know works? That makes HER2 ideal for testing a new framework.
So, how did we get here? Computational drug discovery isn't new, but the pace of the progress has accelerated dramatically in the last few years. Traditionally, finding a drug candidate meant physically synthesizing thousands of compounds in a lab and testing them one by one. It's a process called high throughput screening. And while it works, it's slow, expensive, and generates a lot of waste. You're essentially guessing and checking at a massive scale. What changed is that we can now model the problem computationally. You can take a protein structure, simulate how different molecules bind to it, and predict toxicity, all before you ever set foot in a lab. AI pushed this even further. Instead of screening molecules that already exist, generative models can now design entirely new ones from scratch, shaped specifically for your target. The question shifted from which of these 10,000 molecules should we test to what molecule should we create. That's fundamentally a different and much more powerful starting point. The lab still matters. You eventually have to validate everything experimentally. But now you only send your best candidates there. AI decides what's worth putting in the lab.
There is a problem. We know that all of these powerful tools exist. P2Rank can find binding pockets on a protein surface. Defect can generate candidate molecules. Autodoc Vina can score how well they bind. AdMetLab can predict toxicity and pharmacokinetics. IBM RxN can assess whether a molecule can actually be synthesized. These are all real, well-validated tools, but they were never designed to work together. If you want to run this workflow today, you need to install each component separately, manually convert files between incompatible formats at every stage, and have enough expertise in computational chemistry to know what you are doing at each step. That's a significant barrier. A researcher in biology or pharmacology who wants to explore a new protein target shouldn't need to spend weeks just for setting up the infrastructure. That gap between the tools that exist and an integrated workflow that anyone can use is exactly what we are trying to close.
So, this is what we designed. The input is simple. A protein structure identified by its PDB ID, which is just a standard public database identifier. From there, the pipeline runs through 6 stages automatically. First, the raw protein data is cleaned and prepared. Missing atoms are filled in, structural inconsistencies are solved, and the file is converted into a format that downstream tools can work with. Second, P2 rank analyzes the protein surface and identifies the most likely binding pockets, the cavities where a drug molecule could attach. Third, Defect takes that protein information and generates candidate molecules in 3 dimensions. This is a generative step. It's not pulling from a database, it's creating new structures shaped specifically for that pocket. Fourth, Autodoc Vina ducks those candidates into the pocket and scores each one by binding affinity, measured in kilocalories per mole. The best scoring pose moves forward. Fifth, AdMed Lab evaluates the winning candidate across more than 200 toxicity features. Can it be observed? Is it toxic? And how does it behave in the body? And sixth, IBM RxN for chemistry checks whether the molecule can actually be made in a real laboratory. There is also an optional similarity validation step using RDKit, where you can compare your generated molecule against known ligands to get a sense of whether it's chemically reasonable. 1 input, 6 stages, and 1 output.
One of the most important decisions we made in designing this was to make it modular. Every stage is an independent plugin. If a better molecule generation model comes out tomorrow, and this field moves fast, so it probably will, you can swap it without touching anything else in the pipeline. We have already found alternatives. Defect could be replaced with RF diffusion. Autodoc Vina could be replaced with Nina. The architecture doesn't care which tool is in each slot, as long as it accepts the right input and produces the right output. And while we are demonstrating everything using HER2, there is nothing HER2 specific about the pipeline itself. You could point it at any protein target with a publicly available structure and run the same workflow. In terms of next steps, the immediate priority is the complete end-to-end implementation, automating the hands-off between all 6 stages so the pipeline runs without manual intervention. After that, we want to test it on a range of different protein targets to validate that it works as we intended. And our ultimate goal is to move the top candidates toward wet lab validation, actually synthesizing and testing the molecules the pipeline produces. We also see potential here beyond research. This kind of framework could be useful in educational settings, for students learning computational drug discovery or drug design competitions where you need to move quickly from a target to a candidate.
So, to wrap up, drug discovery is slow, expensive, and fragmented. The tools to fix that exist, but they are not connected. We've designed a 6-stage modular pipeline that takes a single protein structure as input and runs it through pocket detection, molecule generation, docking, ADMET analysis, and synthesis planning, automatically in sequence. HER2 is our demonstration case because it's well studied and gives us solid benchmarks. The next steps are implementation, generalization, and eventually experimental validation. That's the work ahead of us. Thanks for listening, and we are happy to take any questions.
Okay, thank you for your presentation. Is there any
Thank you.
question? Okay, we have no questions, so we can proceed to the next presentation, I guess.
Hi everyone.
Okay. Okay, you can start.
Thank you. Can you see my screen? Hi, hello everyone. My name is Mehmetcan Angün, and today I will present our study titled Automated Detection and Size Classification of Pneumothorax in Chest X-ray Image using a deep learning-based clinical decision support system. This work was conducted at İzmir Katip Çelebi University in the Department of Biomedical Engineering under the supervision of Dr. Özlem Karabiber, Cura. What is pneumothorax? Pneumothorax is a potentially life-threatening condition caused by air accumulation in the pleural space. If not diagnosed rapidly, it may lead to respiratory deterioration or lung collapse. Although chest X-ray are widely used, detection of pneumothorax can sometimes be difficult because radiographic findings might be settled, especially for a small pneumothorax case. Additionally, emergency departments often experience heavy workloads, increasing the possibility of delayed diagnosis. Therefore, AI-based clinical decision support systems may help radiologists by providing faster and more consistent screening. The main aim of this study is to develop a computer-aided diagnosis system capable of automatically detection pneumothorax and estimating its severity. Our system consists of two stages. In the first stage, the model determines whether pneumothorax exists on the chest X-ray. The second stage, detection pneumothorax cases are classified according to their size as smaller than 20% or greater than 20%. This distinction is clinically important because treatment strategies may differ depending on severity. In this study, we used posterior and anterior chest X-ray images. The dataset contains 700 healthy images and 470 pneumothorax images. The pneumothorax images were equally divided into two severity groups, case smaller than 20% and greater than 20%. This balanced severity distribution was important for the second stage severity classification model. This slide shows the overall framework of the proposed system. First, chest X-ray images are preprocessed and resized. Then, three independent CNN architectures analyze the images. Their predictions are combined using a majority voting strategy. If pneumothorax is detected, the image is forwarded to the second stage severity classification model. Finally, the system produces a clinically meaningful output. We use three different CNN architectures: ResNet 50, ResNet 101, and DenseNet 121. ResNet architectures are effective because residual connections help prevent vanishing gradient problems in deep networks. DenseNet 121 improves feature reuse by connection layers densely and is frequently used in medical imaging tasks. All models were trained under the same pre-processing and optimization settings for fair comparisons. Instead of relying on a single CNN architecture, we used an ensemble strategy. Each model independently predicts whether pneumothorax exists. The final class is determined using majority voting. For example, if two models predicts pneumothorax and one predicts LT, the final output becomes pneumothorax. This approach improves robustness and reduces dependence on a single model's weaknesses. The first stage achieves strong pneumothorax detection performance. The ensemble system reached 96.3% accuracy, 95.1% sensitivity, 97.4% specificity. High sensitivity is especially important in a clinical screening because missing pneumothorax case may have serious consequences. These results indicate that the proposed system may support early screening and reduce missed pneumothorax case. In the second stage, pneumothorax cases were classified according to severity. The model distinguished between cases smaller than 20% and greater than 20%. The system achieved 92.8 accuracy and F1 score of 0.92. The height F1 score indicates balanced classification performance between the two severity groups. This stage is clinically meaningful because larger pneumothorax case may require more urgent intervention. To improve interpretability, we applied GradCam visualizations. GradCam highlights image regions that influence the model's decision. Incorrectly classified image, the CNN architectures generally focused on the pneumothorax regions. However, in misclassified case, the attention regions were often inconsistent. These visualizations helps evaluate model reliability and improve clinician trust. In this picture, we can see each model assigned 3 regions, correct regions and wrong regions. The proposed system demonstrates high overall performance and strong robustness through ensemble learning. However, detecting small pneumothorax remains challenging because subtle radiographic findings and harder for the models to learn. Another limitation is the relatively limited dataset size, especially for subtle pneumothorax case. Future studies may include larger multicenter datasets and transformer-based architectures to improve generalization. In conclusion, this study demonstrates that deep learning-based system can successfully detect pneumothorax and classify its severity from chest X-ray images. The ensemble CNN strategy improves robustness and reliability. Additionally, the severity classification stage provides clinically meaningful information for treatment planning. Overall, the proposed system shows strong potential as an AI-assisted clinical decision support tool. Thank you for listening. If we'll be able to answer your questions.
Is there any questions? Okay, we can proceed with the next presentation with Yasrab Memon.
Shall I, Hocam?
Yes, you can start.
Okay. Are you able to see my screen? Hello? Hocam, are you able to see my screen?
Yes, we can see.
Okay.
You can start, Yasrab.
Okay. Good morning, everyone. Today, my name is Yasrab Memon. Today, I will present my work, Healthcare Plus, a resilient mHealth ecosystem for auditory-based adherence and offline emergency system. This work was done in the collaboration of, with the Aytuğ Hocam and Nezihe Hocam. Our study focuses on the elderly-centered mobile healthcare system, where especially for the elderly aging in place scenarios, where elderly people can live their lives independently and safely in their homes. The main idea of this study is to improve the accessibility and the reliability of the elderly people in healthcare management systems. So we will discuss in this in this presentation, we will discuss about the problem statement, the research problem, the research question, and the proposed system and the implementation of our application. So before discussing about the proposed system, let's understand why this problem matters. Aging population. Today, as we all know, global elderly population is increasing rapidly. Because of this, there is a growing demand for the aging in place solutions. And the other problem is the fragmented apps. As we all know, there are a lot of the applications in the market for elderly people, but the problem is most of them are the fragmented app. Like one application is used for the medicine reminders, and the other application is used for the emergency SOS, and the other is used for the exercises or maybe healthcare tracking. So this so managing multiple applications can create the confusing and mentally draining for the elderly people. This creates the cognitive burden and the app fatigue. The other problem is the accessibility. The elderly people who are 60 plus or maybe 70 plus, they experiences the hearing decline. So standard notifications are sometimes easy to miss, or maybe they are too soft that they maybe missed it. And the other problem is the connectivity gaps, like in emergency systems. Mostly emergency systems, they are heavily depend on the internet connectivity. So, however, during the emergency situations, they might internet might not be available in the rural areas. So these problems. So because of these problems, we asked this question: research. Can a single elderly-centered mobile health ecosystem combine accessibility-aware reminders and offline emergency support while reducing the cognitive burden? When we reviewed other existing applications, we have focused that, we noticed that they all focus on the one specific problem. Like maybe one application is focusing on the medication reminders, and the other is focusing on the emergency SOS, and the other is focusing on the hydration monitoring. So we need a solution which has all those application features integrated. What's missing in these is the accessibility-aware reminders, offline emergency communication, integrated daily health workflow, and the low cognitive overhead designed for the elderly people. So let's talk about our contribution. Our first contribution was the integrated health hub. Instead of having multiple applications separately for the elderly people, we have combined all the in one place, like medication reminders, healthcare monitoring and reminders, exercises, health tracking, and the SOS, all in one application. The other contribution is the accessibility reminder. Like our application supports the loud ringtones and or spoken voice prompts, like it's time to take your medicine, or maybe it's time to drink your water, like this. And user can also see the visually, like have they missed the medicine or not. Like they do not need to remember that whether the medicine is like whether they have taken the medicine or not. The other contribution is the offline capable SOS. Like without internet connection, user can send their current location to their guardians. Like the elderly person can send their location to the guardians. We have tested, sorry, we have tested all those contribution. We have did the validation of all those contributions, and they all are working. Let's do the detailed comparison of our application with other existing solutions. Applications such as WeFit and SmartCare, they work well on the wellness related support. Like they provide us the wellness related support, but they heavily depend on the internet connectivity and also provide the standard notifications. The other application is the mHealth, which provide the medication support, but it has just the one single domain. The other application is the ROCA. It provides the emergency SOS support. It also provides us the internet connectivity, which is good, but it does not provide, it lacks in the routine integration, and also it provides the standard notifications. The other application is the medication reminder and the hydration reminder functionality, but it does not provide us the emergency SOS. So our key observation of this finding is that existing systems provide us solutions, but separately. Our application Healthcare Plus combines accessibility, reliability, and routine integration all in one unified solution. Let's talk about the workflow. When user download our application from the Play Store, only then they need the internet connectivity because of the login process, like authentication process. When user log in into our application, they do not need any internet connectivity. This is the dashboard when user will log in into our application. All the features are available at one place. They can like one important design principle was reducing the cognitive load. We followed elderly-centered design principle, cognition over recall. I will discuss about this feature when we will talk about the medicine reminder feature. The minimal navigation process, visual status, and the error prevention, and the last one, accessibility aware interaction. Let's talk about the architecture. The system was intentionally designed using an offline first approach. At the front-end level, we have used the Flutter and Dart technology for cross-platform. Like for we have to do just one code, and that one code would be available, like provide the functionality of the, like we can use the Android phone and also the iOS applications, like one code for both Android application and the iOS applications. For state management, I have used the river code and provider for smooth navigation process. For local storage, I have used the SQLF Lite. For offline data persistent, like user do not need the internet connectivity in order to gain the saved data and see the results, like the charts, and we will discuss later in the slide. And for the GPS, like for the safety and SOS, for GPS, I have used the GPS coordinates. And then I have put those coordinates into the Google Maps so that I do not require the internet connectivity to fetch my current locations. I have used the GPS coordinates from my mobile, and user can send their current location without using the internet connection. The last one, the Firebase authentication. Here we only need the internet connection in the login and the account setting while doing the login and account settings. Let's talk about the key modules of our application. First, medicine reminder. When user enters all the details about their medicine, they have a choice to select between the loud ringtones or maybe the voice, like it's time to take your medicine, according to their preferences. And when they have selected and their medicine is scheduled, if they have missed the medicine, they will get the red alert that your medicine is missed. And if they have taken, they can see in the green highlighted that this medicine is taken. So here the principle recognition over recall applies here. Like they do not need to remember whether they have taken the medicine or not. And the last one, if the application is not active, it works in the background, like application is not open, but they will get the notification that it's time to take your medicine, and they get the notification even if the application is closed. Let's talk about the hydration and monitoring. Same as the medicine reminder, this works exactly the same, but here user can see how much water he has intake for per day. And also user have the choice to do the custom settings, like they have a choice that they can select that after every hour they get the reminder to drink the water. And here they can also do the do not disturbance settings, where at the night and in the morning they do not get the notification that it's time to take your it's time to drink your water. Here they also have the choice to choose the spoken voice or the loud ringtone according to their preferences. And these simple guided exercises were designed for elderly people, and here they also see how much time they have did their exercises, and they also get rewarded in this too. The other module is the health tracking. Here user can keep track of their vitals for the months, even for the year, and they can see their the vitals, like the blood pressure, heart rate. They can see those in the chart also, as the visual representation is easy for them to understand and keep record. They have to enter these these vitals manually. Now the last one is the offline SOS workflow, the emergency SOS button. Let's discuss about here. When first user have to enter the emergency context, so they have a two choice. They can directly select from their they can import from their phone contacts their emergency contact number, and they can manually enter the number of their guardian. And there is an option for the primary contact, like the if they select the primary contact, the call will forward it to that contact number at the time of the emergency. So there, as much as guardian they can save, but there will be only one primary contact whom the call will be forwarded at the emergency. The other feature is that when user will press the alert button, there is a 10-second countdown, because this application is for the elderly. They have mistakenly pressed this button. So after 10 seconds, the location will be sent to all the contact numbers, and the call will forward it to the primary contact if user is not going to cancel the alert button. And this one is working without the internet connectivity, like they can get the Google location without having the internet connectivity. So I have validated all my features in the Android smartphone and also the emulator. I haven't tested in the iOS because Mac OS wasn't available. And the objective of our application was to objective is to test whether the offline SOS is working and the reminders are working on the time or not, whether I am able to save my data or whether I am able to see my charts and all these. So the results were successful. Everything was working perfectly fine, 10 out of 10. I was able to get the exact location of my exact my current location without internet connectivity. I was able to see the logs, like if I am missing my medicine, I was getting the red alert. The only limitation was there was like user has to enter their data manually. So in future, we will work with the wearable watches so that they do not have to enter their data manually. And we will also integrate the AI personalization for the elderly people. So this will be our future work. Thank you so much for listening me. If you have any question, you can ask me.
Okay, thank you for your presentation. Is there any question? Okay, we can proceed to the next presentation. The next presentation will be done with by Fevzi Şimşek. You can start, Fevzi. The title of the presentation is Web-Based Sports Equipment Recognition Infrastructure and Design of a Health Support Module. Okay, if you are ready, you can start.
Merhaba hocam. Sesim geliyor mu?
Merhabalar. Evet.
Ekran da geldi herhalde.
Evet, uygun başlayabilirsiniz.
Hocam. Merhaba hocalarım ve değerli dinleyiciler. Ben Fevzi Şimşek. Bugün sizlere yazılım mühendisi tezli yüksek lisans programı kapsamında hazırladığım projemi sunacağım. Çalışmamın başlığı web tabanlı spor ekipmanı tanıma altyapısı ve sağlık destek modülü tasarımı. Temel olarak derin öğrenme yöntemleri kullanarak açık hava spor aletlerini otomatik tanıyan ve kullanıcıya sağlık desteği sunan uçtan önce bir sistem geliştirdim. Danışmanlarım Fatma Günseli Çıklaçandır ve Samet Çıklaçandır. Öncelikle şehirlerimizde açık hava spor aletleri giderek yaygınlaşıyor. Pek çok farklı çeşitli spor ekipmanları mevcut. Ancak bu ekipmanları tanımayan ve doğru kullanmayı bilmeyen kişiler için hem verimlilik hem de güvenlik açısından ciddi sorunlar teşkil ediyor. Mevcut dijital sistemlere baktığımızda yalnızca birkaç ekipman türünü destekleyen sınırlı çözümler olduğunu görüyoruz. Ve bunların çoğu kapalı spor salonları için yapılmış çözümler. Açık spor aletleri içinse yanlış kullanım sakatlanma riskini doğrudan arttırıyor. Bu problemi çözmek için 12 farklı ekipman sınıfı otomatik tanıyan 7 farklı derin öğrenme modelini karşılaştırmalı olarak değerlendiren kullanıcı profiliyle sağlık takibini entegre eden uçlu açı bir web sistemi geliştirdik. Hedefimiz park ziyaretçilerinin spor aletlerini doğru tanımasını ve güvenli kullanmasını sağlamak. Veri setimiz 12 farklı açık hava spor aleti sınıfına oluşuyor ve toplamda 5178 görsel içeriyor. Bu alanda internette bir veri seti olmadığı için görselleri ben danışmanlarım ve Katip Çelebi Üniversitesi Biyomekanik Mühendisliği öğrencileri tarafından bireysel olarak toplandı. Daha sonrasında veri setindeki fotoğrafların arka planları temizleyerek hem arka planlı hem de arka plan halleriyle işleme dahil edildi. Burada 12 tane sınıfımız yer alıyor. Bunlar sırasıyla abdüksiyon, bel esnetme, bilgisayar, çiftli yürüyüş, kolomuz, leg extension, leg press, mekik, step, üçlü vücut, uzay yürüyüş ve yan salınım olarak yer almakta. Veriyi %80'ini eğitim, %20'sini test olarak böldüm. Genellenebilirliği güçlendirmek için hem holdout hem de tenfold cross validation uyguladım veri seti üzerinden. Kısaca sistem mimarisinden bahsedecek olursam da ön yüzde Angular Single Page Application kullandık. Kullanıcı buradan fotoğraf yükleyebiliyor, sonuçları görüntüleyebiliyor ve sağlık takip modülüne eriştirebiliyor. Arka planda REST API ve Python ile bir REST API servis bulunuyor. Burada JWT token'la kimlik doğrulama, kullanıcı profil yönetimi ve PostgreSQL entegrasyonu yer alıyor. Görüntü işleme ve yapay zeka modülünde ise TensorFlow ve Keras ile inşa edildi. Transfer öğrenme yaklaşımı benimsendi. Kullanıcının yüklediği görüntü 224'e 224 piksel boyutuna getirilip normalize edilerek modele besleniyor. Model 12 sınıf üzerinden olasılığı hesaplayıp en yüksek olasılıklı sınıfı ve güven skorunu döndürüyor kullanıcıya. Model karşılaştırmasına baktığımızda da öncelikle holdout üzerinden gidelim. 7 farklı derin öğrenme modelini aynı veri seti ve aynı koşullar üstüne karşılaştırdık. Bu modeller Connextini, EfficiencyNet B0, MobileNet V3, ResNet 101, MobileNet V2, EfficiencyNet B3 ve ResNet 50. Değerlendirme metrikleri olarak da Accuracy, Precision, Recall, F1, ROC, AOC ve eğitim süresi ve çıkarım süresini kullandım. Burada holdout veri setinde en yüksek doğruluğu %89.75 ile Connextini elde etti. Bunu %89.07 ile EfficiencyNet B0 ve %88.78 ile MobileNet V3 izliyor. Burada connectivity en yüksek doğruluğu verse de eğitim süresi yaklaşık 6 saate yakın sürdü. Çıkarım süresi de 190 saniye. Bu rakamlar diğer modellerle kıyaslandığında çok yüksek çıktı. Örneğin EfficiencyNet B0 ise sadece 1237 saniyede eğitildi. 27 saniyede de çıkarım yapabiliyor. Burada da detaylı metrik tablosu yer almakta. Bahsettiğim gibi connectivity'de eğitim süresi ve model süresi çok yüksek çıktığı için tenfold cross validation sonuçlarına baktığımızda da holdout testinin tek bir veri bölünmesine bağımlı olmaması için tenfold cross validation uyguladım. Bu yöntemde veri 10 eşit parçaya bölünüyor. Her seferinde 9 parça eğitim, bir parça test için kullanılıyor ve sonuçlar ortalaması alınıyor. Tenfold cross validation sonuçlarında EfficiencyNet B0 öne çıktı. %90.38 accuracy, %89.32 F1 skoru ve %99.32 ROC IOC ile en güçlü genellenebilirliği gösterdi. Burada not olarak Connextini'yi kullanamadım. Tenfold Validation'da süre çok daha uzun süreceği için diğerinde 6 saat sürmüştü. Burada bunu dahil etmedim. Holdout ve Tenfold Cross Validation sonuçlarını birlikte değerlendirdiğimizde de en verimli sonucu EfficiencyNet B0'ın en dengeli ve güvenilir model olduğu ortaya çıkıyor. Ben, sistemin çalışma mantığından bahsedeyim. Ekran görüntüleri de vermek istedim. Kullanıcı Angular arayüzünden fotoğrafı yükleyebiliyor. Eğer mobilden giriş yapıyorsa kameradan çekebiliyor. İkinci adım olarak Fast API backend görüntüyü alıyor. Analize göndermek için ön izleme çıkıyor. Üçüncü adım TensorFlow modeli 224'e 224'e boyutlandırıp normalize ediyor ve kullanıcıya doğruluk oranı ile birlikte çıkan sonucun doğruluğunu teyit etmesi için bir seçenek sunuyor. Burada hayır derse tekrar görüntü yükleyebiliyor. Dördüncü adım ilgili spor aletinin doğru kullanışı ve hangi kas grubunu çalıştırdığı gibi bilgileri gösteriyor. İsteğe bağlı olarak giriş yapılarak da kullanılabiliyor. Bu giriş yapıldığında da kullanıcı sağlık modülü, sağlık takibi ve aktivite takibi gibi özellikler yer alıyor. Elde ettiğimiz bulgulara baktığımızda birkaç önemli çıkarım çıkıyor. Holdout test setinde en yüksek doğruluk connectivity'deydi. Ancak hesaplanma maliyeti nedeniyle kullanım için çok uygun değil. Çapraz doğrulamada Efficiency Net B0 en güçlü genellenebilirliği sundu. Hem hız hem de doğruluk dengesi açısından en pratik tercih bu model. Hız odaklı baktığımızda MobileNet V2 ve MobileNet V3 çok daha kısa eğitim süresiyle %87 üzeri doğruluk elde etti. Sınırlı kaynakla çalışacak bir sistemde bu modellerde tercih edilebilir seviyede. 7 modelin tamamı %85 üzerinde bir doğruluk oranı sergiledi. ROC ve AOC değerlerinin tamamı %98 üzerinde. Modellerin sınıflar arası ayrımı son derece güçlü yaptığını gösteriyor bu da. Sonuç ve bu çalışmada gelecekte yapılabilecek çalışmalarla ilgili. Bu çalışmada 12 sınıftan uçtan uca bir web sistemi geliştirdim. 7 model karşılaştırmaları olarak değerlendirdik. En iyi holdout doğruluğu %89.73 ve connectivity ulaştı. Holdout ve tenfold cross validation birlikte kullanılarak sağlam bir validasyon süreci oluşturuldu. Responsive tasarım sayesinde sistem hem mobilde hem masa üstünde çalışabiliyor. Gelecek çalışmalar kapsamında ise buradaki sınıf sayısı arttırılabilir. Mobil uygulama geliştirme ve kişisel takip sisteminde daha fazla özellik eklenmesi gibi şeyler yer alıyor. Bu proje aynı zamanda bir TÜBİTAK projesi, biyomekanik mühendisiyle geliştiriliyor. Ben bunun hem backend tarafında hem de ön yüz tarafında yer alıyorum. Dinlediğiniz için teşekkür ederim. Sorularınız varsa alabilirim.
Çok teşekkürler sunumunuz için. Herhangi bir soru varsa alalım. Soru yok sanıyorum. O zaman okay, we can proceed to the next presentation. Title of the next presentation is Security Grid, the Critical Imperative of Cyber Security for Electric Systems. The presenter will be Alkanza Abdallah. Are you there? Mohammed Alabadi is there, I guess. So, will you make the presentation? Okay, maybe we can wait for several minutes.
Hocam bölüyorum ama sunum yapan arkadaşların kameraları açması gerekiyor. Şimdi kimin sunum yaptığını görmüyoruz.
Başlayabiliriz herhalde, değil mi? Okay, if you are ready, you can start.
Hello, it's okay now.
Okay, start, please.
Can I start?
Yes.
My subject about securing the grid, the critical imperative of cybersecurity of electric system, and analytical exploration of operational and strategies. I will start. The core problem, modern electric grids are complex cyber-physical systems, or we call CPS. Between theoretical security models and practical implementation, there are three layers from transition from isolated infrastructure to separated physical systems and the integration of digital control. Convergence of unprecedented technological innovation and escalating security risk. Driving forces of transformation. Smart meters enabling two ways of communication efficiency. The system of SCADA supervisory control and data acquisition for remote monitoring. Internet of things is different of industrial Internet of things. This promises greater flexibility and resilience. This photo about SCADA and Internet of Things and Industrial Internet of Things. The paradox of connectivity. Main argument as the grid's intelligence and connectivity and consequence of vulnerability. The big problem about national security and economical stability and public safety. We will talk about economic stability, financial distribution from power outage. Evolving nature of physical vulnerabilities, analysis of how threats target both the digital control layer and the physical equipment layer. The review about the expanding attack surface due to increased entry points. This diagram about communication links and how the system operator and how the end user, like electric vehicle customer or another customers, how connect and what the AI and digital connection or IIoT or also IoT, Internet of Things. This connection between power transmission and distribution. This time, what mean AGC, automatic generation control, and another, what's this meaning for all? Continue meaning of like DOS, meaning denial of service. This also is very important for our research. And ED, like economic dispatch. And load frequency control, call it LFC. Summary of what this all means. The previous diagram appears a cybersecurity threat map for a smart grid or power system, also showing vulnerabilities, attack vectors, and targets across different layers of the power infrastructure. This means from number 1, system operator level. Number 2, power generation. The power generation attacks on control devices like HMI, PLC, RTU, network, MITM, DOS, and malware threats. Number 3, transmission and distribution. 4, electricity market. This risk about pricing and dispatch system like EMS, LMP. Number 5, customer service provider attacks on metering, SM, MDMS, and EV, and customer data phishing, MITM. The overall theme is cyber physical system in the power sector, highlighting how attack can move from IT system to physical grid operations, affecting reliability, economics, and safety. Also, this diagram about identify how we protect and detect what will the respond and how well will recover. Lessons from the past notable incidents. The review about incidents like synthesizing historical cyber attacks on electrical systems, implications, discussion how past failures inform current defense strategies. The example about Ukraine attack summary. There was 225 K, that means thousands, and 3.5 hours and 135 megawatts, its field of power. I will talk about the connection, how the attackers make no electricity in some regions. This title about Ukraine attack summary. Cyber attack on December 23, 2015 that caused a widespread power outage. 3, it means the number of regional power distribution companies that were successfully compromised and attacked, like this, the names of companies, and 225K, that means 225,000 customers or end users who lost power as a direct result of the attack. 3.5 hours, this meaning the duration of power outage for the majority of affected customer, approximately 3.5 hours. 35 megawatt, the amount of electricity load in megawatt dropped or lost from the grid due to the attack. 100 likely refers to hundreds of the thousands additional customers who experience the distribution or indirect effects. 10 could refer to dozens of substations that were forced into manual operation or taken offline. 50, this often cited figure, represent the number of substations that had their control system compromised and were remotely switched off by the attackers. Core strategy frameworks evaluating international and national standards for grid defense practices, proactive monitoring, and real-time threat detection. Emerging research leveraging AI and optimization for self-healing system. In this diagram also will appear the transmission control center and distribution control center and energy provider and the distribution resources, distribution power electronic and distribution substations, transmission substation and connection with generating stations. This all communication network between them. Resiliency enhancement start from planning and response and restoration. 3 layers of depend on from generation to end user and distribution and transmission. This about prior to an event and during an event, after an event. This all of how happened and how will respond according to attackers, or how the incident focused, and post-incident learning. Here, like some example from U.S. electric grid from 2025, AI starting intelligence is very high and expanding to autonomous operations. And 2029 ecosystem will appear. Talk about how the sustainable energy and integration of renewable energy source and grid security measures. I'll talk here about cyber resilience as a challenge in the energy industry. Cyber criminals have the skills to create large-scale blackouts, which have severe socioeconomic remote function for individuals and business. Cyber attacks on power already succeed in causing significant temporary blackout, and a comprehensive strategy to mitigate the proportional damage is required. Technological grid advancement are a double-edged sword regarding cybersecurity. The increased digital and decentralized technology provides a large attack surface, which means protecting the power supply more aggressively. The U.S. Department of Energy has called for close collaboration with the private sector to strengthen security measures and share information, focusing on 3 principal areas: strengthening preparedness, coordinating response and recovery, accelerating research and development of resilient delivery systems. What conclusion securing the future? A great cybersecurity is not an IT issue. It is an operational imperative for modern society. The lights going out is bad. Cascading societally collapse is catastrophic. The path forward, sustained investment, adherence to evolving standards, a skilled, adaptable workforce, unwavering collaboration across the energy ecosystem. Summary: a great security is no longer just a technical issue. It is a strategic necessity. The imperative for collaboration between government, academia, and industry. Commitment to continuous innovation in defensive technologies. Thank you.
Okay, you may complete your presentation again. Is there any question?
Any question?
Okay, thank you for your presentation. By this presentation, we have completed the session. Thank you for your all presentation.
Thank you.
Lütfen fotoğraf için kameralarınızı açabilir misiniz? Katılımcılar lütfen fotoğraf için kameraları açar mısınız?
Efendim?
Nasıl tüm arkadaşlar belirliyor fotoğraf için?
Okay. Can you hear me? All the participants? Could you please open your cameras? Seninki mi? Benimki mi açık şu anda?
Şimdi
Okay, okay.
herkes nasıl fotoğraf için? Biliyorum nasıl.
Kapatayım. Aynen buraya test açıldı.
Tamam. Sen orada.
Ne açılmadı? Ha, şurada. Açtı herkes. Görüntüleri.
Aldım.
Okay, thank you very much.
Thank you. Bye.
Thank you.
Thank you. Have a nice day.